Welcome to another video from explainingcomputers.com. This time I'm going to talk about quantum computing, which sometime in the 2020s may become the most powerful kind of computing available. I first made a video on this topic over 5 years ago, but since that time, and particularly in the last 18 months, quite a few things have happened, and so I thought it was time for an update. Now I want to say from the start, this is not going to be a deeply technical video. I'm mainly going to focus on the practical things which are being achieved by companies like IBM. But this said, I thought we should start out with the basic overview of the concepts. Conventional or classical computers are based on millions or billions of miniature transistors. These can be turned on or off to represent a numeric value of 1 or 0. In turn, this allows classical computers to store and process data using binary digits or bits. In contrast, quantum computers work with quantum bits or qubits, which are represented by the quantum mechanical states of subatomic particles. Due to the strange laws of quantum mechanics, qubits can exist in more than one state or superposition at exactly the same point in time. This allows a qubit to assume a value of 1 or 0 or both of these numbers simultaneously. In turn, this enables a quantum computer to process a far higher number of data possibilities than a classical computer. The fact that qubits can be in more than one state simultaneously is exceptionally weird. Flip a coin, and it cannot come up both heads and tails at the same time. And yet the quantum state of a qubit really can do just that. In addition to assuming superpositions, qubits can become entangled. Entanglement is another quantum mechanical property and means that the state of one qubit can depend on the state of another. This is useful and powerful, as it means that observing one qubit can reveal the state of its unobserved pair. By relying on these strange quantum mechanical properties, future quantum computers should be able to tackle computational challenges that cannot be handled by traditional hardware. Such challenges are likely to include molecular modelling, which may lead to medical advancements and the development of new materials. Future quantum computers should also help to solve logistical problems, as well as enabling the development of far more sophisticated deep learning artificial intelligence. Quantum computers are also likely to be used for code breaking and in cybersecurity. Many large computing companies are now working on quantum computing, and indeed IBM has been researching quantum computing for over 35 years. And in May 2016, IBM made a 5-qubit quantum computer publicly available on the internet, which means you can go to the IBM Quantum Experience website and you can click on Library to access all the manuals and learn all about it, or you can go to the Composer tab and you can actually access a real working quantum computer. And already this has been used to run over 300,000 public experiments. Now, in March 2017, IBM created a new division, IBM Q, which is going to develop and make available commercial quantum computers which will access over the web from the IBM cloud. And in May 2017, IBM announced 2 new prototype quantum processors, a 16-qubit processor which is now available over the web from its Quantum Experience website, and a 17-qubit processor which is going to be the start of its commercial quantum computing ventures. It's still a prototype, but it'll be involved in delivering the very first, very early commercial quantum computing services over the web. And it doesn't stop there. IBM hopes in time to develop a 50-qubit processor. And this is significant because a 50-qubit processor should be able to achieve what's called quantum supremacy. In other words, a 50-qubit processor should be more powerful than any traditional, any transistor-based computer ever created. Another impressive quantum computing pioneer is D-Wave Systems in Canada. In 2007, D-Wave demonstrated a working 16-qubit quantum computer, and then in 2011 they became the first company in the world to actually sell a quantum computer when they sold a $10 million 128-qubit machine called the D-Wave 1 to Lockheed Martin. In 2013, D-Wave next sold a 512-qubit machine called the D-Wave 2 to NASA and Google to establish the Quantum Artificial Intelligence Lab at the Ames Research Center in California. By 2015, D-Wave had broken the 1,000-qubit barrier with its D-Wave 2X, and in January 2017 sold the first 2,000-qubit machine, the D-Wave 2000Q, to a cybersecurity firm called Temple Defense Systems. Now, despite all of these milestones, the work of D-Wave systems remains controversial. And the reason for that is they use what's called adiabatic quantum computing, what's called quantum annealing. And this approach to quantum computing has been dismissed by many others in the field, not least IBM, who call it restrictive. IBM have even called it a dead end. Now, to explain what all this means without getting deeply technical, in an IBM system, they use what's called a gate-based approach. In other words, they actually have control of the qubits in their system. The same way that if you've got a transistor-based computer, you can control the flow of electrons in the transistor. But in a D-Wave system, in a quantum annealing system, you don't have that type of control. So you might be thinking, how do D-Wave actually make their quantum computer work if they haven't got full control of the qubits? And the answer is they take advantage of the fact that all physical systems tend towards a minimum energy state. What does this mean? Well, it means that if I make a cup of tea, it'll be boiling hot, but if I leave it on the counter for an hour and come back to it, it'll be stone cold. Or at least it'll be the same temperature as the surrounding environment. It would have tended towards a minimum energy state. And what D-Wave do is they take advantage of the fact that the qubits in their quantum computers will also head towards a minimum energy state. So while they can't actually directly control them, they do know what their behaviour is going to be. And therefore what D-Wave do is they express all the problems they give to the quantum computer, all the algorithms they give it to solve, they express them all as energy minimization problems. And yes, that is restrictive. They can only run certain types of algorithms, but it has allowed D-Wave to create the systems it has to start selling them and to have more qubits than anybody else. But you can hopefully now understand why this is controversial. This all said, there has been some very good evidence recently that the D-Wave systems are functional and useful for certain types of purposes. Not least, this paper was published in 2016, and according to this paper, the D-Wave systems can run certain algorithms up to 100 million times faster than a conventional computer with a single core processor. So that is a pretty good result, and it's worth pointing out that everybody who wrote this paper, who did this research, actually works for Google. Talking of Google, in addition to being a customer of D-Wave systems and having bought several of their quantum computers, Google is also developing its own quantum computing technology. And this is a kind of hybrid between the machines being made by IBM based on a gate-based model and the machines being made by D-Wave systems based on quantum annealing. And right now, Google is testing a 20-qubit machine based on its technology, and by the end of 2017, it hopes to be testing a 49-qubit machine, or in other words, a quantum computer approaching a point of quantum supremacy. Now, the other interesting thing that's happened recently linked to Google is that in March 2017, this paper was published in the science journal Nature, and a lot of the authors of this paper are Google engineers. And I think you can take this paper to be a statement of intent from Google about the importance of quantum computing. This was published in the same month that IBM announced IBM Q, their own commercial quantum computing initiative. And in this paper, the Google engineers are arguing they must invest very heavily in quantum computers because, as they say in this paper, within a few years, well-controlled quantum systems may be able to perform certain tasks much faster than conventional computers based on CMOS or complementary metal oxide semiconductor technology. Just in case you're wondering, Microsoft is also working on quantum computing with an initiative called Station Q. And this is basically backing lots of different quantum computing projects around the world in different labs and also on its own campus. And it's particularly focused on a technology called topological quantum computing. In December 2016, Intel also revealed plans to create quantum computers using silicon qubits inside transistors on traditional silicon wafers. In other words, Intel is trying to make quantum computers work based on the silicon chip technology it obviously knows very well. And a final company I would note is Alibaba. Alibaba is the biggest e-commerce player in China. And in July 2015, Alibaba teamed up with the Chinese Academy of Sciences to form the CAST Alibaba Quantum Computing Laboratory. And as one of the professors involved in this explained, the CAST Alibaba Quantum Computing Laboratory will undertake frontier research on systems that appear to be the most promising in realizing the practical applications of quantum computing. Quantum computing is based on extreme engineering. For example, the quantum processors at the heart of the D-Wave and the IBM systems I've discussed in this video have to be supercooled down to almost absolute zero, down to almost the temperature at which atoms stop moving. And that type of thing is never likely to happen in the home or in most workplaces. So we can be fairly certain that quantum computers will always be constrained to the data center. And in turn, that tells us that quantum computers aren't going to replace all traditional computers. Indeed, nobody in the industry expects that's going to happen. But clearly, what the big computing companies do think will happen in the next decade or so is that quantum computers in the data center will start to complement traditional computers and will allow them to start offering new types of services, new types of security services, new types of scientific services, but also new kinds of artificial intelligence. So it's perfectly possible that maybe in 10 years' time, you'll be having a conversation with a digital assistant, something that's a descendant of something like Amazon's Alexa or Cortana, and that digital assistant will be running on a quantum computer. So in maybe a decade's time, many of us will spend our days talking to quantum computing systems. And so, with that thought, that's now it for this video. I hope you've enjoyed what you've seen here. If so, please press that like button. If you want to know more, I've left loads and loads of links down in the video description. If you haven't subscribed to this channel, please subscribe, and I hope to talk to you again very soon.